So chapter 14, part 2, we're going to start talking about something called life histories. And we'll be talking about this for several slides. So basically, life history is a summary, it's kind of like a description of all of the important aspects of a species with regard to four important concepts. So these are the four concepts that you're going to learn about life history. And you can think about it as the history of life. I think the term is a little awkward, but it is what it is. We have to deal with the term, and the term is life history. So there's four important parts, like I just said. The first one is how old is this population on average when they first reproduce? So we're going to be thinking about that as part of their life history. The next one is an interesting one. It's what is the probability of surviving and of reproducing at every age that they're alive for. And when I say age, it doesn't necessarily mean years in age. It can just mean months, depending on the species that we're talking about. The next one is litter size. And it'll get a little awkward when we're talking about humans because we will apply this concept of litter size. Litter size just means how many babies you're having at one time. For humans, it's generally one, right? On average, it's one. We'll also talk about litter frequency, how often you are able to, as a population, reproduce. And then finally, we will be talking about longevity, how long that population is able to live. So those are the four, we call them life history summary characteristics. And all of these life histories are shaped by natural selection. So we're going to take a look and go through these three variations. They're very, very common variations of life history patterns, and they have different names to them. So the first one that we're going to talk about is called slow, gradual reproductive investment. And I want you to keep in mind, just going back here, maybe it'll be helpful for you to write these down, that we're going to be dealing with each of these four topics for each of the various patterns that we'll be mentioning again on the next slide. Okay, so thinking about these four, I just mentioned to you slow, gradual reproductive investment. And the example that I'm going to step through with you is the greater bulldog bat. And the greater bulldog bat is an animal that reaches sexual maturity at 1 year of age, which is our first life history characteristic of age at first reproduction. So that's 1 year old. It reproduces about one offspring every year, and that's the number 3, litter size and frequency. What about probability of surviving and reproducing at each age? That was the second thing on our list. And it turns out that there's not a lot of predators on bats. So the probability of surviving and reproducing at each age is pretty good. You got a good chance of making it to the next year. And then the next one on the list, the fourth one on the list, was longevity. How long do they live? The greater bulldog bat can live for quite a long time, definitely longer than 10 years, not longer than 30, I believe. So that's the four variations in life history. The next one that we're going to talk about, the pattern is called Big Bang reproduction. And our example is this little creature right here called Antechinus, which is a marsupial living in Australia. And we're going to go through the four things again. So the age at first reproduction is 1 year, just like the greater bulldog bat. It says that it mates intensely over a 3-week period. That's not essential as one of our four things in our list of life history characteristics, but it is important for understanding the next thing, which is that shortly after that 3-week period, males die. They die, they're dead. This is one of the reasons we call this Big Bang reproduction. They literally just have sex and then they die. So that is their probability of survival and reproduction. That's the second thing on our list. Survival and reproduction at each age, and the answer to that is the probability of surviving for the males is non-existent. And for the females, they actually die after their litter is complete. Their litter size and frequency, they have a big litter size, Remember, our greater bulldog bat only had one in the litter. So we have 6 to 10 in the litter here for our antechinus, and frequency is once in their lifetime. And longevity clearly is 1 year. So this is going to be a big difference between the slow, gradual reproductive investment that we see in the greater bulldog bat and the big bang reproduction. Major difference, even though the sexual maturity is the same age, there's these other differences, and that affects their life history pattern. We're going to talk about our last life history pattern, which is called fast, intensive reproductive investment. Yes, these are terms that you need to know. They're not just descriptors, they're terms. So please make sure you learn them. And we're going to use as our example the house mouse. And so the house mouse will reach sexual maturity at 1 month of age. So that's the first point on our life history characteristics, is the age at first reproduction. The house mouse is 1 month old. And then it says it produces litters of 6 to 10 offspring every single month. So that's the number 3, litter size and frequency. That's reproducing like crazy, really. What's the probability of this house mouse surviving? And the answer is kind of in the picture, right? We've got this cat, it eats this mouse, like everything eats the house mouse. Birds of prey eat it, your neighborhood cat eats it, foxes, any coyotes, everything's eating the house mouse. So the probability of surviving to reproduce again is very low. And then the longevity, I guess if you have a house mouse as a pet, I mean, some people do, so good for them. I don't want one, but if you like that kind of thing, that's great. You can have them and they can live in a little cage for several years. But in nature, they tend not to live more than a few months at a time. So that's kind of thinking about the different versions there of our life history variations. That, again, the list of 4 things is really important, and I think I've gone through each of them with you. Hopefully you wrote them all down because I don't have everything listed on this page. So, before I go on, which one do humans exhibit? Which of these variation in life histories do humans exhibit? Are we fast intensive, big bang, or slow gradual? And hopefully you see pretty quickly that we are in fact the slow gradual. We reach sexual maturity at anywhere between these days 12 and 16 or 17. We only produce 1 offspring at a time in general, but of course it's not every year that we reproduce, and a lot of people stop after just 1 or 2 these days. We've got a really good probability of surviving and reproducing until the next time, and we live a really long time. So that fits most into the slow, gradual reproductive investment that we see like the bat. So why is all this variation exist out there? Is there any one strategy that's better than another strategy when it comes to evolutionary outcomes? And the answer is absolutely not. There's lots of possible responses to all these challenges that species face. Like how are you going to respond if you've got a lot of predation? How are you going to respond about when to reproduce, or how often to reproduce, or how many babies to have? So it turns out that it depends on lots and lots of things. And I'm going to start going through these strategies with you a little bit. So which life history is better for any given circumstance? We have to figure it out by asking a couple questions. And the first question is, what is the cost of reproductive investment? Now, cost makes it sound like money, and at least for humans, money is a stand-in for cost. And we've talked about this earlier when we were in natural selection. But there is a cost of reproducing, and the cost is for anybody that reproduces, any species that reproduces, even plants. There is a material cost to them. Babies are made, even seeds of plants are made from the bodies of the parent. And so the parent has to give material to that offspring in order for that offspring to survive. This makes sense. There's also energetic costs. If you're a plant and you're soaking in the sunshine, you think that's all free energy, but it is energy. And so it takes energy to reproduce. You have to make make the seed, you've got to go through this process of maybe making a flower, those kinds of things. So there's material and energetic costs associated with them. If those costs of reproductive investment are high, then you're probably not going to have as many babies. If the cost of the reproductive investment is low, then you can have lots and lots and lots of babies. Make sense? Good. Okay, so the next one is also extremely important. What is the individual in the population? What's their likelihood of surviving to have future reproductive episodes? So if you're a house mouse, your likelihood of surviving to reproduce again is not very good. But if you are a redwood tree, your likelihood of surviving to reproduce is very, very good. And so depending on what the likelihood of surviving is, that makes a difference about which strategy of those three that I talked about on the previous slide back here, which of those strategies makes the most sense. Just remember that natural selection doesn't just favor short-term reproductive success. It favors your overall lifetime reproductive success. So you might be putting out tons and tons and tons of seeds, but if you do that right before a frost, you're not likely to actually have successfully reproduced. You've just made seeds. So timing is a big deal there. Natural selection is favoring overall lifetime reproductive success, which we call fitness. What about humans? How does humans fit into all of this? And again, we have a low probability of dying in any given year, which means that this gives us the luxury of not reproducing when you're very, very young. You know, we just talked about when humans go through sexual maturity, that's puberty, that starts around age 12 on average. But most people aren't having babies, thank goodness, at age 12, right? We're deferring that until years and years and years down the road. These days, at least in the United States and other developed countries, that age is in the young 20s on average. But there's lots of people who are reproducing later in life as well. So because we have a low probability of dying, because there's not much things that are killing us off, we can defer reproduction. It also allows us to have one offspring at a time and put tons of investment, tons of cost, material cost, energetic cost, into that parental effort. So what we do when we do this is we maximize the likelihood of that one or few of our offspring that they will actually survive to reproduce themselves. Back in the day when there wasn't a lot of modern medicine, people had a lot more babies because the probability of surviving, for the offspring surviving, wasn't that great. These days, it is much, much better for us. We can measure that kind of thing that I've just talked to you about, like probability of surviving into the next generation and our human life history by looking at something called life tables and survivorship curves. We can do this for any species, and population ecologists do look at these kinds of tables for lots of different species. If you look at this life table here, you can see that it's not for a human. And the reason that you can tell it's not for a human is because the age only goes up to age 15. So clearly at age 15, all of the individuals are dead. And so this is not humans. But in general, these life tables do allow us to predict the likelihood of dying at any particular age interval. And this is the kind of thing that actuaries do for life insurance. So again, looking here, we start out with an initial population of 210 individuals being born. Their age is 0, so they're born. And the proportion of them that are alive when they're born is 100%. I guess that makes sense. In the next column, you see how many have died in that interval. And it was 140 individuals died in this population, which gives an overall probability of 67% dying. So you got a 67% chance of dying if you belong to this species. And then the next age interval is age 3. So skipping ahead 3 years, you've only got 70 individuals in the population. That's 210 minus 140 and give you 70. The proportion alive is now 33%. So you get another 28 of them dying, which turns out to be right around 40% of them dying. Now, if you added up all of these, it doesn't add up to 100%. It's for each individual age interval that we're looking at these percentages for. 3 years later, you've only got 42 individuals in the population. That's 70 minus 28, that gives you 42. If you'll notice here, these always do go down. So we've got 20% of the population now alive. Another 28 deaths go by, that gives us a 67% chance of dying. Again, just following through here, you can kind of see the pattern. And if you look right here, this life table is giving you a clue about my next slide. It's talking about the survivorship curve called the type 2 survivorship curve. And let's just move on to that so you can see what I'm talking about. So if you were to graph these survivorship chances over time, and that's this one right here, this column right here, what you see for a type 2 is this kind of slow, steady decline in population size over time and survivorship over time, to eventually you're down to 0 of the ones that were born in that original interval are still alive. So type 2 is a steady, regular pace of death. That's as opposed to type 1. And type 1 is interesting because at the beginning of life, for individuals that follow the type 1 survivorship curve, there is a slow, very slow die-off when the individuals are young. See, like these are dying off much faster, but it's a steady die-off. Here, they're not dying off very much until they reach like a certain age, and then all of a sudden, bam, the population crashes. So, like turtles are a great example of this because they can live a really long time with only a few individuals in the population dying. But when they reach a certain age that we're going to start to call old age, the population of individuals, they don't live very, very much longer past that. That's a type 1 survivorship curve. Slow, long, oops, I'm sorry about that. Long-lived in youth, not many dying, but then old age is reached and then bam. The third type of curve here is called the type 3 curve. And the type 3 curve is the inverse of the type 1 curve. What you have here is a lot of individuals dying when they're young, and then they reach kind of this critical age where the death rate slows. And the death rate here is still declining. Nobody lives forever. No fish or anything else lives forever. But once they reach a certain age, the probability of them dying decreases significantly. For our fish, that's because almost everything is going to eat a small fish, right? They're just eating them up like crazy. But when the fish get to be a certain age, they get to be a certain size. And it's harder for the fish to be eaten because they're so big. So once they get to be that age, they stop being preyed upon quite so much. And so they got a pretty good chance of surviving for quite some time after that's reached. So that's a general pattern of survivorship curve. You got your type 1, like the turtles. You got your type 2, like any birds really are type 2. They've got a regular pace of death throughout their life. And you got your type 3, fish are a great example of type 3. Everything eats a small fish, but once it reaches a certain size, it doesn't have as many predators. So what are humans? Which type of survivorship curve are humans? And it always surprises me when I ask this question what my students think. So a lot of my students think that we're type 2. Not all of them. But that's like thinking 67% of babies die, and then 67% of teenagers, and so forth and so on. You got this low, steady rate, and that's just not how it works. We, as humans, are type 1. Most babies survive. Most teenagers survive. Most adults survive. But of course, there's a slow decline as time goes by. And then we reach old age, and then once you reach old age, then you're dying off really fast. So humans are type 1. And so we have a long life expectancy. That's another thing that this curve shows us, is that we as humans have a long life expectancy. I went ahead and grabbed this image off the internet. I think it's very interesting and very telling. This is how long are you going to live if you've already reached age 65? And these data were collected back in 2011. So once you've reached age 65, how long are you going to live? And the answer is it depends on whether you're a man or a woman, and it depends on what country you live in. So if we look at France, the men will live 19.3 years past age 65 on average. The women will live 23.8 years past age 65 on average. Sorry, guys, but you probably already know this. Men do not live as long as women do. And in part, that's because of testosterone and damage that testosterone does to your heart, and so forth. Heart disease is a big killer of men, more so than women. If we go down this list, France is number one. They have the at least in 2011, they had the highest longevity, and followed by Japan and Spain and Italy. So we're just gonna go down this list. You can see Korea, Portugal, Austria, Finland. There's Canada right there. Iceland, Norway, Sweden, Germany, Israel, the Netherlands. There's England, the United Kingdom. The OECD 34, that's just the group average. And the group average is about, for women, is about 20 years. But if you look, the United States is lower than the average, and we're far down the list of these countries, of these developed countries. It's kind of weird how low we are. We think, as the United States, we think we're like among the best countries in the world. And don't get me wrong, I think we are, but not when it comes to longevity. What is it that we are doing so very wrong that these other countries up here seem to be doing much, much better? And there's lots of things that go into this, including healthcare. All of the countries up here have universal healthcare, and we don't. So that's a big deal, because if you don't have healthcare, then you're not taking care of yourself. Uh, as a country, we tend to be more obese than these other countries, and maybe that has to do with our lifestyle, our general level of stress, those kinds of things. But all of them have to do with our basic healthcare processes, and we're not so good at it, unfortunately. Hopefully, we'll get better at it. I think it's important that we do, because hey, we're number one. All right, so that's just kind of food for thought. My next question for you is, can you maximize life history traits? Can you be the best at reproduction, at survival, at having babies, and at living a long time? Can you be the best at those? Lots and lots of offspring, beginning right after you're born, continuing all the time. Here, this one's interesting. I'm going to throw it in. We haven't talked about it yet before. Growing tremendously large, because the larger you are, the less likely you are to be preyed upon, kind of like we saw with those fish earlier in that example. And then, of course, living forever. And, and of course, can all these life history traits be maximized? And the answer is no. It is literally impossible. And the reason that it's impossible is because you only have a certain amount of material and a certain amount of energy. Remember, I used those terms before when we were talking about reproduction. There's only a certain amount that you get in your lifetime. And so if you're putting a lot of that energy into making lots of babies, then you're not going to live for a long time. If you're putting energy into growth, then you're not going to be able to have a lot of babies when you're young. Does that make sense? So we call these trade-offs, and specifically we call them evolutionary trade-offs. It's not possible to have all of those things occur. So there's only so many things that you can allocate your resources to. You can allocate them to growth, you can allocate them to reproduction, and there's lots of different parts of reproduction, like when you mate, number of offspring you have, the size of your offspring, all those things are about reproduction. Or you can allocate that to survival. You literally, think about a big pie chart. You literally cannot allocate everything 100% into those three categories. You've got to If you're going to grow, then maybe 50% of your energy is going to go to growth. That means you're not going to reproduce as much. And maybe you won't be surviving as long. Does that make sense? Okay, so let's look through a few examples of these trade-offs. So hopefully this will make a little bit more sense. The first trade-off that we're going to talk about is a trade-off between reproduction and survival. And this is pretty clear. The Big Bang reproducers that we talked about before, which were the antechinus, you remember the little marsupial thing that looked like a rodent? That's not a rodent, but it's a marsupial. So they were Big Bang reproducers. Salmon, like in this picture, are Big Bang reproducers. What they do is they put a huge investment into reproduction. It takes so much energy for salmon to swim upstream and then lay their eggs that they immediately die afterwards. That's Big Bang. So it's a trade-off. They're not putting their energy into survival, they're putting their energy into reproducing. The next one is a trade-off between reproduction and growth. And lots of trees do this. Humans can do this too. I'll talk about it in a second, but let's talk about trees first. What we notice in trees is that trees don't reproduce every single year. Some trees don't, some do, but some trees don't, like the beech trees. Uh, every 2 or 3 years they're going to reproduce. And if you cut down a beech tree, you can look at their growth rings, and what you see is that the years that they reproduced, they have smaller growth rings. And the years that they held off on reproducing, they have bigger growth rings. Trees only have so much energy that they have. It seems like they can get all this energy from the sun, true, but they've got a limited number of leaves. And so they cannot reproduce and grow maximally. They've got to put the energy into one or the other. It's a trade-off. It's an evolutionary trade-off in the life history categories. The third one that we're going to talk about is a trade-off between the number of offspring and the size of offspring. And you see this trade-off happening a lot in lizards. So lizards lay eggs, and this particular lizard is called Euta stansburiana. That's how you say that. So these guys produce medium-sized eggs, and they produce a medium amount of them. So that's like in contrast where like some lizards will do lots of eggs, but they'll be small. Or some lizards will do a few large eggs, and the larger the egg, the better the chance of that offspring surviving, but not always. Lots of small eggs, there's not as much yolk in there, they don't have as good a chance of surviving. So Euta here, stansburiana, they've settled kind of on the medium strategy. So if we go back, I just want to go back here and talk about humans and reproduction and growth. It turns out that for females that reproduce when they're young, it does happen. Sometimes you have a girl having a baby at a very young age, 12, 13, 14. This does happen. And what we see is that for that woman, she will not grow as much during that pregnancy. And so women who reproduce at a young age tend to be shorter than women who hold off on that reproduction. So even in humans, there's a trade-off between reproduction and growth. Okay, so still thinking about our life history traits, and we're almost done thinking about our life history categories. We're in the fourth one now, and that is longevity. So when we think about longevity, we think about the aging process. And the aging process is, it's kind of strange actually, because when you're born, you are born with some genetic diseases. And if you happen to have a genetic disease that kills you before you reproduce, you're not going to pass that genetic disease on to your offspring, right? Because you're dead. So any allele that causes sickness and death early in life is not going to be passed on, right? Hopefully this makes sense. However, and here's where things get kind of interesting. If you have an allele that causes sickness and death that you don't get until after you've reproduced, then you're born You grow up, you've got that allele. It's gonna cause you to die eventually and get sick eventually, but you have a baby, and that baby inherits that mutation, and so and then you die here. So what I'm trying to say is that it turns out that things like aging, gray hair, wrinkles, brittle bones, all these things that we associate with aging are actually alleles that cause sickness and death later in life. Those characteristics, you're passing them on to your offspring before you express them, before they actually kill you. I think this is really fascinating. So aging is simply the cumulative effect of the buildup of late-acting harmful alleles that we call aging. And you will pass those on to your offspring, and there's nothing that's going to stop you from passing on that from your offspring. I mean, I guess you could have a mutation that causes death at age 150, but you won't know that until after you've had your babies. So I think that's really interesting. So why does it that some, like all species age? You need to understand this. Grays and slowing down and brittle bones for animals and things along those lines. All species age, even trees age. So what determines the longevity of a species? Like, why is it that some species don't live very long? And by the way, even mice show signs of aging after only a few years. So what is it that determines longevity in this species? And it turns out it's all about hazard, environmental risk. If you live in a high risk world where there's tons of things coming by and eating you, and you got a high chance of death at an early age from an external source, and that's forcing you to reproduce early, because if you don't reproduce early, then you're not reproducing at all, then you are going to age at a young age. Because you have reproduced early, you've already passed that trait on to your offspring. If you live in a low risk world, though, where there's not a lot of predators, where individuals tend to reproduce later, that means that you're going to live longer and you're going to show signs of aging later in life. So what determines longevity in a species turns out to be hazards and risks. What are your chances of dying? If your chances of dying are really high, you're not going to live very long. But not just because of the predation, also because of what we talked about here with this aging thing, right? Because of this, once you reproduce, you've passed on that trait, and the accumulation of those cumulative effects of those late-acting alleles is going to really come into play. All right, well, this is a good place to stop, and I'll see you in the third video.